Okay, last we left off, we were talking about acid-base dissociation. We also were talking about dissociation constants. Okay, so your Ka represents your acid dissociation. So you're having your acid dissociate to the hydronium ion and the base.
See all of them.
What was that?
We can see all of them instead of the one.
You can still see all of them instead of the one. Okay, so I'll send a message because for some reason it should be fixed on my end. I just deleted them all.
Yeah.
Maybe try refreshing your.
No, I mean on your screen, all the slides instead of just one.
Oh, okay. It's the wrong side.
Sorry.
Okay, that's all right.
No, I updated the what you call it.
Okay, let's see.
Now
what about now? Is that better?
Yeah.
Okay. Yeah, me and Zoom. Me and everything lately. I feel so computer illiterate sometimes, you know. And I think I'm pretty good with computers. Okay, so as I was saying, the Ka is going to be the equilibrium constant for dissociation for acids, and the Kb is going to be the equilibrium constant for dissociation of base. Now, again, when we think about this, we've got to think about it in terms of when that acid dissociates, that acid is going to dissociate into the hydronium ion and that particular conjugate base. Okay, so in this case, it's just represented by A minus. So we know that anything that's liquid, solid, or gas, we never take in consideration for the equilibrium constant. We only take in consideration things that are pressure or that isn't true. So liquid, solid, and I guess gas. So you won't take solids or liquid into consideration, but you will take gas into consideration in line. In this case. So we're going to take things that have pressure and things that are in aqueous solutions, because those are the things that are going to be readily mixed, and they're going to affect that equilibrium constant. Does that make sense?
Yeah.
Yeah. Okay. So when we look at our Ka, it's just setting up that equilibrium constant the same way. Even though we call it the constant of dissociation, it's the same thing that we're going to be doing. We're going to have the products over the reactants, and we're going to use the coefficients as our exponent. So in this case, if there were a 2 here, then we would have a 2 as our exponent. But in this case, it's a 1, so we don't have to worry about it, right? So it'll just be the concentration of the hydronium ion times the concentration of the conjugate base over the conjugation of the acid. And then the base is going to behave the same way. Now, because we have that Ka and that Kb, we can sit there and make some assumptions if we have systems that are similar to each other, right? So like, for instance, when we talk about the acid dissociation in the context of the base dissociation, right? We know that we're always going to end up with that water product, right? We're going to end up getting water. And so if we take the dissociation of the acid and the dissociation of the base, it should equal to another constant, which is we call Kw, which we've already known from before. And we know that our Kw, if we sit there and did the equation, putting them together, our Kw is just going to be the product between the K base and the K acid. Okay, and so there is a big old table, like in the old days we would use table. Now you guys are going to use Google, that are going to give you listings for all of the different acids, the dissociation constant for all the different acids that exist. Okay, so usually you're going to have a table in your book. You have a table that has the Ka, your constants for your dissociation constants for your acids, and also your dissociation constant for some of your bases. Okay, so how do I use this? So calculate the Ka for the dissociation of 0.1 molar hypochlorous acid solution with equilibrium of the hydronium ion. So in this context, we're going to do exactly the same thing that we've done before, right? But now we're given our Ka, right? I believe. So we're calculating our Ka. And so how would we set up the equation for our Ka? Since we know the equation, the general equation for dissociation of an acid. Oh, I'm just talking, huh? You guys aren't seeing anything.
You just closed out of it.
Okay.
It's back up.
Okay, so how would I set up the equation for the equilibrium constant? What is it? Come on.
It's products of the reactants.
It's the products of the reactants. Okay, so if we're talking about the equation, the chemical equation for this acid, we have hypochlorous acid. What does hypochlorous acid look like? Hypochlorous acid. Brush up on that nomenclature. Let's see, who am I going to pick on?
Hypo is one less. Where's my papers?
Okay, it's one less than if it was
It.
if it was it. That's right. If it was it, like so or sulfite instead of sulfate, right? So, and then it'd be one less of sulfite. But if we're talking about chlorous, so what does chloric acid look like? Anybody?
Wouldn't it be HCIO?
HCl, chlor.
CL.
Yeah. Oh, that's right. HClO. So that is going to be hypochlorous acid. Okay. And we know it's an acid, so it's aqueous. Right.
Yep.
So you can sit there. Are you guys here? Can you hear me?
Yeah.
Okay. Okay. So we could sit there, and at this point, we have the option of, we could do it the old-fashioned way where we actually put the water there, right? Or we could just use that aqueous. It would mean the same thing. And we know that we're going to yield what are we going to yield? Remember, dissociation of an acid. What's removed from an acid when it dissociates?
Water.
No, we have water. Water. What makes an acid an acid?
H plus ions.
H plus, that's right. H plus. So we're going to get the H plus plus our conjugate base, ClO minus. Good job, Kayla. Okay, so is it balanced?
No.
No, it's not balanced.
No, because you have 2 hydrogen on your reactant and 1 on your product.
Okay, so maybe we should do it like this. Instead of calling it H plus, we'll call it H3 plus, 3O plus, right?
Oh, yeah, because there's a third. Sorry.
That's right. Yeah. Plus. So which means the same thing as our H plus. Okay.
Okay, what is that supposed to be, Dr. Henry?
I know. Wait a minute.
H3.
I'll fix it.
No, I was like, do I gotta
Leave my kindergarten writing alone. Not picking on me. It's Monday. And then you can set the aqueous and aqueous. Okay, so you said it's the products over the reactants, right? So do that. So we have Ka is going to equal concentration of H3O plus, which is the same thing. So H3O plus is the same thing as H plus. These guys are equivalent. I'll let you guys remember that. okay? And ClO minus over our reactant, which is the acid. Okay, so if we got this, right? It says calculate the Ka for the dissociation of 0.1, so 0.100 molar hypochlorous acid with an equilibrium hydronium ion concentration of 2.38 times 10 to the minus 5. So we know that if we did our ICE table, I stands for what again?
Initial change equilibrium.
Okay, and this is for our HCl, HClO, sorry. This is for our H plus, H3O plus. And then this is for our ClO minus. So we know at equilibrium, this value is going to be 2.38 times 10 to the minus 5. We also know that these values are going to be exactly the same because we know there's a 1-to-1 molar ratio. So this value is going to be exactly the same here. So if we said the change was going to be X, we already know what the value for X is. X is going to be equal to this. Molar. And if we know that the initial concentration of the acid is 0.100 molar, so then the change is going to be minus X. So then at equilibrium, this guy is going to be 0.100 molar. So if we know that X is equal to that 2.38 times 10 to the minus 5. If we subtract that value from that 0.1, this should be minus X, right? So then this value is going to end up being, if we look at this value, so this guy is 10 to the minus 1. Is that true? 0.1?
Yeah.
If I subtract something that is actually, let's do it like this. 0, 0, 0, 0, 2, 3, 5. And we're doing sig figs, right? And we know that this guy is 0.100, right? This value here is so small that it's not going to make any difference, right? If we're using sig figs, we subtract it, we'll end up rounding, you'll end up with 0.999999765, right? So when we round, it's only 3 significant figures, we'd end up with this number again. So this guy is negligible. You can ignore it because it's so small. Okay, does that make sense?
Yeah.
Okay, so then all it is now is plug and chug. We have the values for at equilibrium, so we can just sit there and say that this guy is just going to be 0.10 molar. And then we just plug these guys into this equation. So you'll get Ka equals 2.38 times 10 to the minus 5. And that's going to be squared. Remember, if you guys are plugging into your calculator, to use the parentheses, because otherwise you just square that last number divided by 0.100 molar. Okay. Okay, so then our Ka is going to equal I can't find a calculator. Also known as my cell phone. So 2.35 Okay, so you get Ka equals 5.66 times 10 to the negative 9.
Yep.
Okay, piece of cake.
Yeah. Can you go over that that number again that we could ignore? I didn't really understand that.
Okay, sure. Use a different color there, if it helps out a little bit. Okay, so I'm gonna write down here. So if we have a number, so we have this number, 0.100. Okay. It has 3 6 8s, 1, 2, 3. Okay, and we're subtracting a number that is 0.0000. Let me do it like this. 0.0000238, right? Because this guy's 10 to the minus 5.
Oh, okay, gotcha.
3, 4, 5. Yeah. Okay. Since this number is so small, right? And we're doing 3 sig figs, we draw our lines. This is going to be the line, but this guy is going to be used for rounding, and that's it, right?
Okay,
So
for some reason I didn't put it together that was the number for 2.38 times 10 to the negative 5.
Yeah.
I thought it was a different number.
Yeah, and so it kind of saves us that time, so we don't have to worry about it if that number's so small. And that's that whole thing. It's like sometimes you got to decide whether a number's small enough or is it, and that's it.
Right.
Okay, so let's do the question below it. You guys have to set it up. Tell me what I need to do. I always like starting off with the equation, chemical equation, me personally, because I'm a chemical equation type of guy. Calculate the Kb for 0.100 molar nitric solution with an equilibrium hydroxide concentration of 1.0 times 10 to the 1.50 times 10 to the minus 6.
Nitrite is NO3 minus. Or sorry, it's NO2 minus.
It's NO2 minus. Okay, good job. Is that Taylor?
Yeah.
Yeah.
Okay. So we have NO2 minus. And what are we going to get on the other side? It's reacting with water. So H2O. So then what are we going to get on the other side?
Would we get the hydroxide?
We will get the hydroxide. So we'll get the OH. That's going to be our conjugate base.
And then the H plus.
Is that H plus is going to be associated with
The hydroxide, isn't it?
was it going to be associated with the hydroxide or the nitrate? Because think about it, remember, conjugate acid, conjugate base.
Oh, yeah.
So you're just going to be flipping that guy here. So you're going to end up with this guy, H NO2 AQ. Okay, so just remember, if this guy is acting as a base, it's going to be accepting that H plus. So on the other side, that guy should have an H plus. Okay. Okay, so how will we set up our KB? Can I erase the stuff in red? Did you guys get all that down?
Yeah.
I can use that space up there. Oops. Sorry. Okay, so my KB is going to be equal to what?
Products over reactant.
Products over reactants. Okay, so then we have the concentration of HNO2 plus, oops, not plus, times the concentration of OH minus divided by our nitrate concentration. Okay. Okay, so what are we going to do next?
Do your ice table.
Okay, so we know that starting out, we have concentration for nitrate is what?
Zero point 100 molar.
0.100 molar. Okay. And then our change is going to be represented by our X. And then we know that the equilibrium concentration for hydroxide is going to be
The 1.50.
1.50. And since we know there's a 1-to-1 molar ratio between the two, between the hydroxide and the nitrous acid, then we know that that guy is going to have the same value. And then we know the change here is going to be minus because we're taking away from that guy. So then we're going to end up with 0.100 molar. So then we could just say that X is going to equal 1.50 times 10 to the minus 6. And this value is that a small value or is that a big value compared to that You have to put minus. Is that a small value or a big value compared to that 0.100 molar?
Small?
Small value, so we can
Okay.
ignore it, right?
Yeah.
We can ignore it down here. So when we plug into our equation, over here, we'll get 1.50 times 10 to the minus 6, and that's a 10. Squared divided by 0.100 molar, and that's going to equal 2 molar in there. Okay, so that equals 2.25 times 10 to the minus 11.
Yep.
Okay. Questions, concerns, Cash, Kool-Aid. Okay, excellent. Oops, sorry. Okay, sorry. I did. Okay. Okay, so with the acid-base type of calculations, you're going to do exactly what we did in the prior chapter with general equilibrium. Only thing we're applying it to acid and bases. We're going to go through the same process where we're going to put those X's and as being subtracted from our initial product that has a product, and then compared to that doesn't, right? And we're also going to be using that 5% rule. That 5% rule allows us to sit there and determine whether that number is going to be big enough so that it's going to be significant, or if it isn't going to be significant. Okay. So same process that we had done prior, right? Exactly the same thing that we've done prior, right? So this, we set it up. We have our equation. We set up our initial. We subtract the change. We add the change on the other side. Exactly the same setup. And then we'd solve for X. Okay. Same thing is going on here. Okay. Questions? In the case of the base as well.
No.
No.
Okay, good. Okay, so I'm going to ask you guys to sit there and work these guys out independently, right? Since you guys know it's going to be exactly the same process, okay? And
Okay.
then make sure you guys work it out because it could be to your advantage. Okay. And that's exactly the same case for this next problem as well. Okay, so these are just some more problems to give you a little more work, you know, so work it out. And you guys done a lot of these in your homework, or you should be doing them in your homework assignment. I know not as many as you would normally get. Yeah, I think I gave you like 15 or something like that. Okay, so just to give you guys a little more practice, but make sure you guys try to do some of them because you may see them again, okay? And then the biggest thing that you want to take into consideration is trying to determine what is going to be the acid, what is going to be the base. Like in this case, this is going to be triethylamine solution. That's going to be your base. And then, and that's going to be reacting with water. And then you're going to, on the other side, you're going to have a conjugate acid, okay? So that's the hardest part of these guys here. Here, in this case, so it says calculate the pH of a, and you guys know how to calculate pH. How do you calculate pH? You guys remember how to calculate pH?
No.
No. Wait, hold on. I have it written somewhere in my paper.
Remember, it had to do with the hydrogen.
Right.
uh,
Concentration of the hydronium ion. So
Yeah.
pH is going to equal minus log the concentration of H3O plus. Right. So under these circumstances, the first thing that you want to do is you want to calculate what the concentration of H3O plus is. Okay. So let's do this first one. So calculate the pH of a 0.0220 molar benzoic acid solution with a Ka equal to 6.40 times 10 to the minus 5. So if I'm calculating the pH, the first thing that I'm going to do, I have a Ka. Ka is going to equal the concentrations of the, this is an acid that's going to be dissociating. So we have the benzoic acid at the bottom. So I'm just going to put benzo. So I don't want to write the chemical formula. Benzoic acid. We know that that's going to be separating to the hydronium ion, and then it's going to be benzoate. So we have H3O plus benzoate. Benzoate. Okay, so then I know that I use my ICE table, ICE. I know I'm starting out with 0.0220 molar. So this guy is going to be 0.0220 minus X. I know that this value is probably going to be pretty small, but, and then we have, and that's for benzoic acid. Mind if I just put BA for short?
Sounds good.
Okay, and then we have X. Oops. X here, X here. So this guy is going to be, I'm just going to use B minus, and then we're going to use H3O plus. So then this guy is just going to be X down here. So then we'll get our Ka is equal to this, which is going to be equal to, yeah, I'm going to go down here, equal to X squared over 0.0220 minus x. And then we just solve for x, right? We know the value of Ka. We just plug that in, 6.40 times 10 to the minus 5. Okay, so if we assume that this guy is going to be so small that it's not going to make a difference, so we're going to neglect it. That's that 5% rule. So small. Okay, so then you just get x squared equals 0.0220 times 10 to the minus 5. Oops. Times 6. .4 times 10 to the minus 5. Okay, so, and then we just solve for x. So we do that math. Do you guys feel like you're in a math class yet?
A little bit.
Yep.
Horrible flashbacks. I'm just kidding.
Okay, so I get x squared equals 1.40, or actually 1.41 times 10 to the minus 6. So then I want to take the square root of that. So I get x equals 1.19 times 10 to the minus 3. I check to see if this guy is 5% of our initial concentration. So I just divide that by our initial concentration, divided by 0.2, oops, 0.022. So it's actually 5.3%. So it's over that 5% rule. So that means that I probably have to do it again to get the right number and take this value into consideration in the quadratic formula. Okay, so it was close, but it wasn't close enough, right? So in that case, then we'd have to go through this full equation. So I'm going to erase this here. This part here. Plug in my full equation, and then I'm going to use the quadratic formula. You guys remember the site for the quadratic formula? Did I give you that link?
Yeah.
X. So we're going to bring this all on the other side of the equation. So we'll get x squared plus should be 6.40 x, oops, times 10 to the minus 5 will make our x, so it doesn't look like a times there, plus, oops, minus 1.41 times 10 to the negative 6. Come on, negative 6, there we go. Okay, and then that's going to equal 0. And then we just plug it into our quadratic formula. Mine up. You guys see it?
Yeah.
Okay, so let's plug in those coefficients. Oops, wrong. Okay, so A is going to be 1. B is going to be 6.4 EE, or E to the negative -5. And then this is going to be 1.41 E to the -6. You just hit calculate. I screwed up. I forgot negative here. Oops, not there. Negative. Okay, so we know that X can never be a negative number. So we know that it has to be that one. So then we'll say X is going to be 0.0116 molar. Okay, so then we calculate our pH. pH is going to equal, because that's going to equal the concentration of H3O plus. So that's going to be minus log of 0.0116.
Aren't you missing another 0, Dr. Henry?
0.0.
It was 0.001.
Okay, my bad. I am missing another 0.
Okay.
See, my brain doesn't work always on Mondays either. So it's 0.001. Okay, thank you.
No problem.
Okay, so then that's going to equal, I'll move that down so you can actually see it over the white writing. Okay. And
I got 2.94.
okay, so our pH would be 2.94. Okay, questions, concerns, Cash?
Nope.
Good.
No,
Okay.
I just feel like I'm in a math class.
Yeah.
Can you just make sure that they're under 5%? Ugh.
Oh, believe me, grading it, I feel the same way, but you know, I gotta prepare you for, hope for the best, prepare you for the worst.
Yeah.
Okay, so that's, okay, so we talked about pH. Okay, and let's see, clear. Can I clear this now?
Yeah, I just saved it.
Okay. Okay, and that was just for that first problem. So, and they take a little bit, right? They're not like, there's a lot to them. Okay, so you can calculate the equilibrium constants for these guys too. I mean, sorry, you can calculate the equilibrium concentrations for things as well too, using the exact same method that we did with all of the different steps. So you just want to make sure that you get your dissociation, what's happening in the equation right first, because then that makes it a little bit easier. Does that make sense?
Mm.
So it's the same process, exactly the same
Well,
process.
And you need your equation in order to determine for your ice table, right?
Yep.
For your
Yeah, it makes it, well, you can do it generically, you know, if you know it's an acid that is dissociating, right?
Yeah.
So you know that this is a case of an acid dissociating, right?
Yeah.
And then, so then you can do it generically, but if you have your ice table with that particular equation, it always helps out,
Okay.
at least for me. Like, I'm a very visual person. It makes sense to me.
Okay.
Okay. Okay, so then we have the hydrolyzation of salt. So basically, when we get an acid and a base that are reacting, and you titrate it out, and if you titrate it to completion, right? In the case of a strong acid and a strong base, if you titrate to completion, you're always going to end up with water and a salt, right? And then that endpoint is always going to be a pH of 7. Now, if it's a weak acid and a strong base, that's going to end up at a different pH, okay? So in the case of a weak acid with a strong base, it's going to end up producing a weak base, right? So then your pH is going to be slightly different. So you're going to be more on that, rather than being a pH of 7, you're going to end up being a pH that is going to be greater than 7, okay? If it's a strong acid or a strong base, I mean, if you titrate with a strong acid, then you're going to end up with a weak base. And so your solution is going to be acidic if you have a weak acid and a strong base. Then you're going to have a weak acid with a strong base. You're going to have a basic solution. So then your pH is going to be above 7. And in the case of your acidic solution, your pH is going to be below 7. Okay, so depending on what you're titrating with, if you have a strong acid and a weak base, you're going to end up with your equilibrium point to being a pH less than 7. A weak acid and a strong base, it's favoring the base, so you're going to have a pH that is going to be greater than 7. Does that make sense?
Mm-hmm.
Okay. Okay, so this is just basically showing you that. Okay, so if we have a strong acid and a strong base, right, our equivalency point is going to be pH 7, which is water, right? It's going to be perfect. If we have a weak acid and a strong base, then our pH is going to be greater than 7. If we have a strong acid and a weak base, then our pH is going to be less than 7. That equilibrium point is going to be less than 7. Okay, and that equilibrium point in this case is called your equivalency point, you know? So your equivalency point is going to be shifted based upon what you're working with. Make sense?
Yeah.
Okay, good, good. Okay, let me see. Come on now. Okay, so let's see. Let's do some real quick example. Okay, determine the pH effects of a solution with sodium hydroxide dissolved in water. So here you have sodium hydroxide and water acting with each other. What's going to happen? What is going to be your pH? Is it going to be pH greater than 7, equal to 7, or less than 7? So acid, base, or neutral.
So that's a base. It's dissolved in water. Oh. Shit, where did that make-
Don't overthink it. So we know that it's a strong base. So hydroxides are always strong bases. And if you're putting in water, what do you expect your pH to be? Greater than 7? Or is it going to be 7? Greater than 7 or less than 7?
More than 7?
Did you say less than 7 or did you say greater than 7?
Greater than 7?
Greater than 7. It's going to be greater than 7, right? Because you're putting in a strong base into a water, right? So water is always at 7. So you're putting a base in there. So then you're just going to get the pH of that base. So you're going to have a 1 greater than 7. So it's going to be basic. Okay. Determine the effects of a solution with hydrochloric acid dissolved in water.
Less than 7?
It's going to be less than 7. That's right. Okay. What about determine the effects, the pH effects of a solution dissolved with sodium chloride? So if we have Na,
Sodium.
Would it be neutral because it's going to disassociate to the ions?
Cl, okay. So, and it's not going to have an effect. So that Cl isn't going to make HCl on the other side. Is that right?
Um,
Okay. So you're right. It's not going to have an effect. It's going to be neutral in that case. Okay. What about pH effect of barium sulfate?
the two is negative. Would it be more acidic?
No. Do we have it? Is this a strong acid or is it, I mean, a strong acid or a strong base, or is this a weak acid or a weak base? And then you have weak acid, weak base, weak base. All right. So what is going to be the effect?
Is this basic? The barium sulfate?
So the barium sulfate is going to be basic. So you're saying you're going to get so H2 plus OH minus so you're going to get it. In theory, you would assume that it's going to be slightly basic, but it's not going to be. It's going to be weak, basic to neutral. In all honesty, because again, it's that salt. It's going to have very little effect, right? So you're going to have very few of those. So it's going to be a weak base in this case. And that's sort of with the sodium chloride. The same thing is going to happen. It's a weak base, but it's so close to 7 that it's not going to make too much of a difference. What about sodium acetate? Na. O2 plus H2O. What's going to happen? Donate. Think about that water. It's donating what?
A hydrogen. So
It's going to donate the hydrogen to this guy.
So it'd be acidic.
Is it?
I don't know, man.
Because you have where it's going to be free. Who's your free guy?
So it's whatever you're left. Okay, so then that'd be basic because you have hydroxide.
Okay.
So it's basic.
What about this guy? H4 Cl minus. Oops. Plus. What's going to happen in the case of these guys coming together?
H is gonna go.
And then also, actually, this guy's going to be neutral. And I'll explain to you in a second why. Okay, so let's,
Acid
what was that?
with that one because you're gonna get the hydrogen go off with the chloride.
Okay. Actually, you're more going to have this happening, right? These guys are going to interact, or I should say the other way around. You're going to get your H3 plus ammonia.
Mm.
Okay, so if we have ammonia and water, is ammonia and water stable? Or does it break down? Or does it completely dissociate? Or anything like that in water?
It's unstable.
No, it's actually very stable. Ammonia is pretty stable. So the ammonium ion, it has stability, but ammonia is also stable. So once this guy is formed, it's going to stay around. It's not going to completely dissociate back into the other forms. So in this case, you're going to have this guy's going to be slightly acidic because now you have this guy available. Now we know that the chloride ion likes to be single because it's happy as it is, right? So it's not going to want to form hydrochloric acid because that completely dissociates when it comes together. So it comes together, it dissociates, right? So you're going to have them free in solution. That's the same thing that's going to be happening here, right? So these guys are also going to all end up being free in the solution. So you're going to end up, these guys are going to completely, as soon as they form. So then in this case, you're just going to end up with this guy and water plus H2O plus your barium, right? So in this case, that pH, because they're going to be completely neutral, and they're not going to want to stay together, that guy's going to end up being neutral in that case. You're not going to have that formation of this acid. So that means that these hydrogens are going to go back to the water because this guy's completely dissociated. Does that make sense?
Yeah.
Yeah.
Think
So
so.
strong acids, we all know that strong acids dissociate. So you're not going to be able to really form a strong acid. It's going to dissociate almost initially. Think contact with each other. Acetate, acetic acid, is a weak acid. It likes to be in this form. So when it has the opportunity to make this guy, it's going to want to do it. Does that make sense? So
Yeah.
that's the reason why this guy would be basic, because then you're going to have these hydroxide ions available.
Okay.
Okay, it's going to be weak basic, but it's going to be basic. And then this guy here is also going to be, this guy's going to be acidic, because now you have this guy available because you're forming this guy. Okay. Okay, so give it some thought, you know. Clear. I have office hours this week. If there are more questions on that, hit me up. Okay, what's wrong? Okay, so some acids can break down to multiple points. So we can dissociate multiple times. Okay, so when we think about H2SO4, right? It has 2 hydrogens that it can get rid of when it's reacting with, when it's in water, right? Thank you. Okay, so let me give you an example. So these are called polyprotic acids. And so at each step, there's going to be a dissociation constant associated with it. The very first one is going to be a very strong dissociation constant. So that means you're going to get complete dissociation. The second one is going to be weaker. The third one is going to be even smaller. So each time that dissociation constant is going to sit there and change. Okay. So the very first one is almost instantaneous. Let's go. Okay. So your first ionization, so getting rid of that very first H, it's going to be instantaneous. So you're going to have a very, very large Ka, right? Then your second one, this is your second ionization, that Ka gets smaller, you know. So then okay, does that make sense? Okay, so if we do the same thing for this guy, for phosphoric acid, what is the chemical formula for phosphoric acid?
HP.
H3PO4 plus water. So this will be that first equation, right? So we'd end up with H3 plus H2 PO4 minus AQ. Second equation, that one's going to be a very fast reaction. The second one is going to be H2PO4 AQ plus H2O is going to yield this one's going to be a little weaker, H3O plus HPO2, HPO4, sorry, 2 minus. My head's working faster than my head. And then in the last case, we have HPO4, 2 minus, AQ plus H2O is going to yield H3O plus PO4 3 minus. Okay, so these These would be the Kas for all of those cases. And so you'd work with the Kas independently, right? Sit there and calculate your concentration calculate your pH. But it's going to be the sum of all of the different OH groups. You know, so it's going to be you're going to have to take into consideration the entire thing, right? Does that make sense?
Yeah.
So you'd use this guy here, and then you'd use this guy here, and then you use this guy here, and then you use all of them together to sit there and calculate how many total hydroxides you have.
Gotcha.
Okay.
So individual.
Yep.
Total.
And what you'll find is that, and I'm going to just give you the hint, these guys are going to make very little contribution because they're so much smaller than this very first one. Look at the size of this compared to the size of this, compared to the size of that. Because this guy is so much larger, your pH is going to be pretty much dictated by that first reaction. Okay. Okay, let's see. Polyprotic. Okay. Questions, concerns, Cash? Okay. One more thing is buffering. I think it's my last. No, it's not my last slide. So basically buffering is basically when you're titrating with a weak acid with a strong base, or vice versa. Weak base with a strong acid, and then you're trying to produce an equilibrium where it's going to be somewhat resistant to pH, right? So then, like, the addition of stuff isn't going to change that pH too much. So that's called buffering. So certain buffers have nice ranges associated with it. So in this case, the buffering reagent is carbonic acid. Carbonic acid is going to buffer that strong acid. And so then what happens is that this buffer could sit there and be really resistant. So that gives you a lot of leeway with the pH that you're working with, right? So it becomes somewhat resistant to it. Okay, so buffers, they're going to be treated the same way that we're treating everything else, right? That we have done before. It's the exact same process. The only thing now, what you're doing is that you're adding that component, and then it's just going to shift that equilibrium, right? And so when we think about Le Chantelier's principle, right, that shifting of things, this is going to be one of those concepts. Okay, we'll pick this back up on Wednesday. So do me a favor, look over the notes, go over this chapter. We'll be finishing up. We have like 2 more slides left, and then we'll start with this question. Okay, I will see you guys later. Have a good day.